Okay, good day to all of you. So before we go through chapter 3, circuit diagrams, so let's have a recap from what you've learned from chapter 2, basic electronics. Okay, we have learned what is a multimeter, and then what are the different electronic components that can be used, specifically in Arduino. And then we have the Ohm's law, how to get voltage, how to get the current, and how to get the resistance, and then how to get power. And then so now we have chapter 3, we have circuit diagrams. So what are we going to learn? So what a circuit is, what open, closed, and short circuits are, then what Fritzing diagrams are, what schematic diagrams are, and what the difference between the series and parallel circuits are. So the question is, what is a circuit? So a circuit is a circular path in which electrical current flows. So the circuit is also the path in which these electrons flow, powering the components that make up the circuit. So the point where the electrons enter the circuit and the current start is called the source. And then of course, the point where the electrons exit the circuit is called the return. So everything between the source and the return, the components and wires that make up the remainder of the circuit is called the load. So for example, we have this switch and this is the light. So this is the so-called load because this anything the components between the source and the return. So as we can see, because the switch is closed, of course, the light will is on. And then of course, when the switch is off, also the light goes off. And then most multimeters have a continuity mode that can be used to test if you have an open circuit or not. If you set your multimeter to continuity mode and touch the two leads together, the meter will emit a tone. Okay, if you're going to use a multimeter and switch it to continuity mode, and then you will hear a sound if there is a if your circuit is closed. If and if there's no sound, it means that your circuit is open. So to test if your circuit is closed or open, put the multimeter into continuity mode and place the two leads from the multimeter at different points in your circuit. And if there is a connection between the 2 points, the multimeter will emit the tone. So that's what I've been saying. If there's a connection or your circuit is closed, meaning there's a continuous flow of electrons or electricity, and then your multimeter will emit a tone. Okay, this is the symbol for the continuity mode. So the most dangerous circuit is a short circuit. A short circuit is one that allows the current to flow through the circuit with little to or no resistance. This is usually a circuit with no load. So, okay, we have an example of a short circuit. Okay, this is a short circuit because there is no resistance. So that's why it's very dangerous. Okay, a schematic diagram, when referring to electronic circuits, is a diagram that contains representations of the elements in the circuit. Each type of electrical component has a standard symbol that is used when representing it on a schematic diagram. So these diagrams will show how each component is connected, given anyone that reads the diagram an understanding of how the circuit works. So okay, we have this schematic diagram, but we have another wiring schematic um, application. This can be used for the Arduino. So we have this Fritzing. So Fritzing is an open source initiative to develop software to design electronic hardware. This software is designed in the same spirit as the Arduino, where it abstracts away the complexity of diagramming the circuit so the user can focus on the design itself. So a Fritzing sketch is a project within the Fritzing application that represents the circuit being created. So, okay, the site for Fritzing is http://fritzing.org /learning. So actually, Fritzing is just a wiring application. there is a newer application that I've only discovered, which is called Tinkercad by Autodesk. It only not just teach you how to design the wiring, but it also teaches you how to code and simulate. So for the sake of learning, since Tinkercad has more features than Fritzing, so we'll have a separate video on how to use the Tinkercad application. So Fritzing diagram, so for the sake of the knowledge for the Fritzing application, so a Fritzing diagram is a picture representation of what the circuit should look like, similar to the open, closed, and short circuit diagrams. The Fritzing diagram has standard symbols to represent each part and a compact design, making it easier to design more complex circuits. So this is an example of a Fritzing um, product, actually an output, in which you could actually create wiring for the Arduino board and breadboard and some of the electronic components that is um, situated, or it is put in the breadboard, on the breadboard. And then next is we have the schematic diagram, separate from Fritzing. Actually, Fritzing also produces schematic diagram. This one is used better for example, if you're not an electronics major and you really want to learn how to wire things in the Arduino board. So this is more convenient. But for electronic hobbyists and electronic majors or engineers, they are more used to the schematic diagram. So while the Fritzing diagrams use images to represent the circuit, schematic diagrams use symbols. This allows for a more compact diagram, which makes it easier to represent complex circuits. So we have the following symbols for the schematic diagram: for the resistor, for the variable resistor, switch, transistor, LED, battery, capacitor, and wire. So another one, this is done from on Fritzing application. So a 9-volt battery, then it's wired to turn on the LED. So this is the corresponding schematic diagram. For this one is we have the 9 volts battery, and then this is the symbol for LED. LED 1, then red, and then we have the resistor, which has a value of 330 ohms. Okay, so next is we have already discussed Fritzing and schematic diagrams. Next is we're going to discuss the parallel and series circuits. So first is a series circuit is a circuit where current only has one path to flow from the source to the return. And then a parallel circuit is a circuit that has multiple paths for the current flow. So let's go first with the series circuits. So we have an example here. So series circuit, it says that the electricity flows only in one path. So this is already an example of a series circuit. Okay, to calculate the resistance in the series circuit, so we have to take note of this. So the total resistance of a series circuits is the sum of the resistance of each component of the load. So actually, getting resistance or the total resistance of a series circuit is just getting the sum of all the resistance of each component of the load. So we have, again, let's go back with the example. So we have the resistor 1, which has a value of 220 ohms, and then we have the resistor 2, which has a value of 330 ohms as an example. So the load consists of two resistors. We have 220 ohms and 330 ohms. So as I've said earlier, that the total resistance of a series circuit is just adding all of the resistance of each component of the load. So we do have two resistors. We have 220 and 330. So what we're going to do, we're just going to add the values of these two resistors. So 220 and 330, I think you don't need anymore any calculator. You can do it mentally. So we have a total resistance of 550 ohms. Okay, it's just easy. Next is we have the voltage. How are we going to get the total voltage of a series circuit? So it is the sum of the voltage of each power source connected in series. So let's go back again in the example. So in the example circuit, there is only one power source, which is the 9 volt battery. Therefore, the total voltage is 9 volts. So another what if, for example, if you used 4 AA batteries consisting of 1.5 volts each in series, rather than the 9 volt battery, we would have a total of 6 volts because 1.5 times 4 is equals to 6, or of course 4 4 multiplied by 1.5 would be equal to 6 volts. So we have 1.5 plus 1.5 is 3, then 1.5 is 4.5, and then 1.5 is equals to 6 volts. So again, to get the total voltage of a series circuit, we're just going to add the voltage of each power source. It is easier if the power source is only one. So if that is the value, then that will be the value. For example, 9 volts battery, so it's 9 volts. Then, for example, if we have 4 AA batteries, 4 times 1.5 is equal to 6 volts. Okay, next is we have the current. So in a series circuit, how are we going to get the current? The same current flows through each part of a circuit. This means that we can measure the current at any point within the circuit, and it will be the same as any other point in the circuit. So in the example circuit, we know that the total voltage is 9 volts. And we know the total resistance is 550. Therefore, we can calculate the current of the circuit using Ohm's law. So we're going to get I, for symbol for current, is equal to volts divided by resistance. So we have 9 volts divided by 550. So this formula would give us a current of 9 volts divided by 550 ohms, or 0.0164 amps. Or um, if you're going to move it, so we have 1, 2, 3. So we have 16.4 milliamps. So that it will have a more significant value. Okay, next is we have the parallel circuits. Okay, I hope you don't have any question with regards to getting values of voltage, resistance, and current in a series circuit. So we have another example. So this is a parallel circuit because there is another path or other paths where electricity can flow. The first path, okay, it can flow in here, or it can flow in this way. So there are two ways or two paths. So we have a 9 volts battery, and then the resistor 1 is 330 ohms, and then the resistor 2 again is 220 ohms. So, okay, is it just the same with the series circuit, or are they different? So let's find it out. So the total resistance of a parallel circuit will always be less than the total resistance of any branch within the circuit, and adding additional branches will always decrease the total resistance of the circuit. So to calculate the total resistance of a parallel circuit, take the sum of the reciprocal of the resistance for each component in the circuit, and that equals the reciprocal of the total resistance. So, okay, this is the formula. 1 over the total resistance is equal to the sum of the reciprocal. So, 1 over R sub 1 plus 1 over R sub 2, 1 plus 1 over R sub 3, and so on, depending on how many resistors you have in the circuit. Okay, so we have an example. So in the example circuit, there are two resistors with values. We have 220 ohms and 330. Therefore, to calculate the resistance of the circuit, we would take the reciprocal. So we're going to convert 220 to 1 over 220, and 330 to 1 over 330, which would equal to 132 ohms. Okay, let's see if it's really 132. Okay, so we have in our example, so that you'll know how to calculate. For example, so let's get 220. Then convert it into its reciprocal, plus we have 330. Then convert it again to its reciprocal. Then we're going to add. So this is the sum. Actually, this is not yet the value because as you could see with the example, with our formula, we have this is only the 1 over r resistance total. To get this, you have to convert it to the reciprocal again. So how are we going to do that? So this is the answer, and then we're going to, as I've said, get the reciprocal of this value. So you will get 132. That's why the answer is 132. Okay? Let's go back. And then next is we have the voltage. So each branch of a parallel circuit will have the same voltage. If we measured the voltage across either branch of the sample circuit, it would show a voltage of 9 volts. So it is easier actually, because either branch of the sample circuit, it would always show a voltage of 9 volts. Okay, next for the current, again, so in a parallel circuit, current will be different in each branch. So the total current of the circuit, or the current coming out of the power source, will be equal to the sum of the current in each branch. So this means that current coming out of the power source will equal the sum of the current running through the 220 ohm resistor branch and the 330 ohm resistor branch. So to calculate current with Ohm's law, we use the formula again, which is I is equals to V divided by R, or V over R, which means the current equals the voltage divided by the resistance. So earlier, in the resistance section, we already calculated the resistance in the circuit was 132 ohms. And we know that the voltage is 9 volts. So the formula is V over R, 9 divided by 132 ohms, or 0.682 amps. Or again, move it 3 decimal places to the right, so we have 68.2 milliamps, to make again the value have a significant value. And then there's another one to calculate, whichever is easier. So we can also use the Ohm's law to calculate the current in each branch, knowing that the voltage for each branch will be the same, 9 volts. So for me, it's the former method is easier because you already get um, the total for the resistance. So the current in the branch that contains the 220 ohm resistor would be, so this is separate for 220, so 9 volts divided by 220 ohms, or 0.049 amps, or 40 point milliamps. If you're going to move the decimal place 3 places to the right. And then another one is get the current for the 330 ohm resistor as the divisor. So the current in the branch with the 330 ohm resistor would be 9 divided by 330, or 0.0273 amps, or 27.3 milliamps. Decimal places, 3 decimal places going to the right. And then what are you going to do? So the um 40.9 milliamps, you're going to add the both of them. So we can now add the current from the branch that contains the 220 ohm resistor to the current from the branch that contains the 330 ohm resistor to get the total current of, we have again, add 40.9 plus 27.3 milliamps, which equals the same, 68.2 milliamps coming out of the power source. So, it depends upon you which is easier, but if I'm to be asked, it's easier with the former because you already got the total resistance. But then again, this solution is longer than the former solution. But again, they're just the same. Okay, next is we have the voltage drop. So voltage drop is defined as the amount of voltage lost through each component in the circuit due to impedance. So what is impedance? It is the amount of opposition that the circuit and component present to the current flow. So actually there is a voltage drop because the circuits or the components has their own resistance. Okay, we have an example here of how of a schematic diagram of lighting up a LED. So we have a power source of 9 volts, and then we have an LED one, and then we have a resistor which is 330 ohms. Okay. To get the resistance is we have to know the voltage of the source minus the voltage of the LED divided by the current of the LED. So we have an example here. So the LED used for this example is we have 3.4 volts and 20 milliamps. Okay, by this formula, so this gives the value 9, which is the voltage source, minus 3.4 volts, which is the voltage of the LED, divided by 20 milliamps, which is the current for the LED. Okay, so getting the value equals to 280 ohms. Okay, what is this 280 ohms? So since resistors do not have a value of 280 ohms, we have to use the resistor with the next higher value, which is 330 ohms as shown in the schematic. So this means that by calculating the needed resistance. So for example, for this one, since it is 280, so for the LED to work properly or so that it will not be burned out immediately, use a higher resistor than 280. Okay, so this is an actual setup of an LED with a 330 resistor, and it is powered by a 9 volts battery. So for the summary, so we are already introduced what circuits are: open, closed, and short circuits. Then describe the differences between, as I've said, closed, open, and short circuits, and then showed how to read a Fritzing a schematic and schematic diagram, and seeing the differences between parallel and series, and creating our first circuit to light up an LED. Okay, with regards to schematic, you have a separate course for this one. So I only focus with what a schematic diagram looks like. I did not really delve into it, deeper into it because as I've said, there is a separate course for you. So then again, as I've said, fritzing is more of wiring. Then there is an application which is Autodesk Tinkercad. I think it will be more useful if you use that because with regards to wiring, Tinkercad has also the wiring capabilities. Okay, so this is it for chapter 3. If you have any questions, okay, you may freely ask me personally or through any means of communication. So again, thank you very much for listening and good day.